I am Dr. Seshadri. Today I want to discuss a topic titled a series RLC circuit. So in this, first I want to connect one resistor, inductor and capacitor. So when AC supply is connected through a series connection of these resistance, inductance and capacitance, the behavior, we can analyze the behavior of the RLC series circuit combination. So this circuit shows the resistance, inductance and capacitance. So when these three are connected in series and given an AC supply of voltage, RMS voltage, then the current will start flowing through this circuit. So let us say VR equal to IR, the voltage drop across resistance equal to current into resistance, that is V equal to IR, voltage drop across IR, and voltage drop across inductor is nothing but the total current into the inductive reactance, and the voltage drop across capacitor is nothing but the total current into capacitive reactance. All these are in units are in ohms. So we know in pure resistor the current and voltage relationship are both are in same phase, and in inductor the current lags the applied voltage V by an angle 90 degrees. If it is a pure capacitor, the current leads the supply voltage by an angle 90 degrees. We know. And let us consider the vector diagram. So here the OA is nothing but the taken as reference. OA is taken as reference, is nothing but voltage drop across resistance, and AD is nothing but the voltage drop across inductance, and BD is the voltage drop across capacitance. So here AB is nothing but AD plus BD. So we want to calculate about up to this AD is nothing but voltage drop across inductance minus voltage drop across capacitance. Now resultant of all this OA and AD will give you the voltage, total applied voltage V. So OD is the total applied voltage V. So the applied voltage V is represented by OD, and it is the vector sum of OA and AD. Therefore, OD equal to OA square plus AD square. OA square plus AD square, or V square equal to IR square, that is OA square, AD in the sense I into XL minus XC whole square. I into XL minus XC whole square. So that is nothing but, after simplifying this, taking I square as common, I square into R square plus XL minus XC whole square, or I square equal to V square by R square plus XL minus XC whole square. Here R square plus XL minus XC whole square under root is nothing but Z, called impedance. So I square equal to V square by R square plus XL minus XC whole square. So current I equal to the total applied voltage V by impedance. So here the term square root of R square plus XL minus X square is known as impedance of the circuit, impedance offered by the RLC circuit. Or another way, impedance square equal to resistance square plus net reactance square. So net reactance here, the total net reactance offered by the RLC circuit is nothing but net reactance. Z square equal to R square plus XL minus X whole square, or that is equal to R square plus XL X square, where X is the net reactance. So here in this case X equal to XL minus XC. X is the net reactance. On phase angle phi, from this vector diagram, the phase angle phi is nothing but, XL minus XC by R, లేదా of R, X by R. XL minus XC by R, X by R. This means the phase angle offered by phase angle phi given by this RLC circuit is nothing but net reactance by resistance. Net reactance by resistance. So phi equal to tan inverse of X by R, tan phi equal to X by R, phi equal to tan inverse of X by R. Tan inverse of X by R. When here there are three cases to calculate the net reactance. First case, when the current lags XL greater than XC, current lags, that means XL greater than XC, first case. And when current leads, in this case XC greater than XL. And third case, unity, that means when XL equal to XC. So three cases. In first case, if the inductance, we know XL equal to 2 pi FL. So if the value of L is high, the value of XL is also high. So the inductive reactance, when the inductive reactance is high for a given RLC circuit, definitely the current lags the voltage. In this case, XL is greater than XC. When XL is greater than XC means, so in this circuit, the net reactance is X. In this case, X equal to XL minus XC. Since XL is greater than XC, so the net reactance will be obviously XL minus XC. This means that the net reactance is inductive reactance. Here the dominating is inductive reactance. So when the inductive reactance is dominating, the circuit, RLC circuit, is inductive in nature. So when in this case inductive in nature, definitely the net reactance will be XL minus XC. Okay, this is the first case. If you apply J operator for this same circuit, same vector diagram, so it is minus JXC, minus J into XL minus XC, JXL. Okay, J will comes into the picture for reactance only, for reactance case. So impedance can be calculated, the phasor sum of resistance and net reactance. Here another case. In this case, when current leads XC greater than XL. So in a series RLC circuit, the capacitive value, if the capacity X equal to 1 by omega C, 1 by omega C. If the capacitance value is low, the Xc will be high. In this circuit, if Xc is greater than the XL, definitely the net reactance will be Xc minus XL. Xc minus XL. So in this case, this is XL, the net reactance offered by the reactance offered by the inductor. In opposite direction, it is Xc. So it is nothing but minus Jxc. So in this case, the net reactance is of capacitive type, capacitive reactance. This means that in this, the capacitive reactance is dominating. So this RLC circuit, this type of RLC circuit is called, is of capacitive in nature. Capacitive in nature. So another case, when XL equal to XC, XL equal to XC, the net reactance is nothing but XL minus XC or is equal to 0. So in this case, only Z equal to R. Z equal to R. Next. So it is seen that if the equation of the applied voltage is V equal to Vm sin omega t, it is nothing but alternating voltage. Then equation of the resulting current of RLC circuit is given by I equal to Im sin omega t plus or minus phi. Here plus for lagging, minus for leading. Plus for lagging and minus for leading. So here the positive sign is to be used when current leads Xc greater than XL. Here reverse case. Here they take here plus for leading and minus for lagging. So generally we write the expression for current I equal to Im sin omega t plus phi. Here plus is used for lagging and minus is used for leading. Sorry, plus is used for leading and minus is used for lagging. Okay. A little bit confusion. Okay. And in general, the current lags or leads the supply voltage by an angle phi. That depends upon the value of R and X. Since we know that tan phi equal to X by R. So here we use J notation here. Later we will discuss about J, operator J. So in this topic, J, if J is considered, Z equal to R plus J, operator J into XL minus XC. Here previous slide we have seen that operator J here. We will discuss later. So here the net reactance equal to J into XC minus XL and J into X minus XL minus XC. So numerical value of impedance Z square equal to R square plus XL minus XC whole square. And phase angle phi is nothing but we know tan inverse of XL minus XC by R. In case of inductive circuit, so its value phi is always tan inverse of XL minus XC by R. And in case of capacitive circuit, the phi value is nothing but tan inverse of XC minus XL by R. And impedance and admittance of AC circuit. So since we know that Z equal to R plus Jx or R minus Jx, here the two components of impedance are resistance and reactance. So here the units for all these impedance, reactance and admittance, impedance, resistance, reactance and impedance are in ohms. The reciprocal of impedance is also called as admittance, reciprocal. So since admittance is denoted by Y, capital Y, and capital Y is nothing but reciprocal of impedance. Here the two components of this Y are nothing but G plus B. Here capital G is nothing but conductance and capital B is nothing but susceptance. So admittance Y equal to G plus or minus JB. So again this G and B and Y, all these terms are represented in mhos. Reciprocal of impedance is nothing but units for impedance are ohms, and units for admittance are mhos or Siemens. Mhos or Siemens. Coming to the triangle of impedance, we know impedance triangle. R is taken as a reference, and perpendicular to that we have to draw XL. XL is nothing but omega L, and the phasor sum of the resultant of these two components, resistance and inductive reactance, will give you the impedance Z. So here phi is the phase angle, and here phi equal to tan inverse of R by XL by R. Also power factor cos phi equal to R by Z, tan phi equal to XL by R. So in this, the impedance, resultant impedance Z is represented by AC, where AB is the resistance in ohms and BC is the inductive reactance in ohms, and the resultant of these two will be obtained by the phasor sum of R and XL, which is nothing but Z, is also called as Z equal to R plus JXL. R plus JXL. Similarly, admittance can be calculated as reciprocal of this impedance, Y equal to 1 by Z. So Y equal to G minus J B. BL means susceptance for inductive circuit. Similarly, impedance triangle. So impedance triangle, if we draw this triangle for capacitive circuit, it will becomes reverse in the reverse direction. XC can be drawn, R is taken as a reference and XC can be taken, and I, both R and I are in same phase in resistance, and in reverse direction it is minus XC, and the resultant of this R and minus XC will give you the impedance. Again, impedance is nothing but Z equal to R minus JXC, R minus JXC. For inductor it is R plus JXC, and for capacitor it is R minus JXC. Again, the formula for impedance is nothing but conductance plus J susceptance, Y equal to G plus J BC. And we will take one numerical problem. A 240 volts 50 Hz AC supply is applied to a coil of 0.8 Henries inductance and 4 ohms resistance connected in series with a capacitor of 8 microfarads. Here we need to calculate the total impedance and phase angle and current. Power factor also, we can calculate power factor also. For this, here the 4 ohms resistance is connected in series with a coil of 0.08 Henries and connected in series with a capacitor of capacitance of 8 microfarads capacitor. So R value is 4 ohms and L value is 0.08 Henries and C is 0.8 microfarads. So RLC is given and applied voltage 240 volts and frequencies 50 Hz is given. Here we can calculate the First we need to calculate the XL value. XL is nothing but omega L. So it is nothing but 2 pi of L. 2 pi into frequency is given as 50 Hz and L is given as 0.08 entries. So 2 pi into F into L. So it is nothing but 25.12 ohms. XC. So XC equal to formula, capacitor reactance formula 1 by omega C. Here it is C, 1 by omega C. 1 by omega means 2 pi F into C, capacitance value 8 microfarads. So 1 by 2 pi into 50, 100 pi into 8 into 10 power 6 minus 6 will give you 398.09 ohms. After calculating this XL minus XC, so first compare. So which is dominating here? So here in this case XC is dominating, that it is 398.09 ohms. XC is dominating 398.09 ohms and XL is 25.12. So we can write, instead of this XL minus XC, we can write firstly we can write XC minus XL. Since XC is greater than XL, we can write like this also. Or so minus of this square will becomes plus. So this will also correct, no problem. This is also correct. XL minus XC also correct. So the total final impedance will not change if the XC and XL are replaced, interchange. So Z equal to 372.99 ohms. So formula for RLC circuit is square root of R square plus X, the net reactance square. So however it is nothing but net reactance. Okay. And after calculating the impedance, immediately you can use the formula I equal to current. Current, we can determine current. I equal to voltage by impedance. So supply voltage is given as 240 volts and Z is calculated 372.99 ohms. Now the current I equal to voltage by impedance, 240 by 372.99. So its value current is 0.643. And phase angle between the voltage and current is nothing but, from vector diagram we can calculate this is R. So this phi can be calculated. Phi is nothing but tan inverse of XL minus XC by R. So tan inverse of XL minus XC we are substituting here and we will get 89.38. So here minus sign for used for leading. So since it is capacitive reactance is more, so the circuit is capacitive in nature. So the power factor is also leading. The power factor is leading. So the circuit is nothing but capacitive in nature. So cos phi can be calculated by using formula R by Z. So R by Z equal to R value 4 and Z value 372.9. We'll get 0.01072 leading. How much power consumed in the series circuit? Power P. So since it is AC circuit, the power formula is nothing but VI cos phi. For DC, the power is nothing but P equal to VI. V into I, voltage into power. Here cos phi will come into picture since it is a AC circuit. P equal to VI cos phi. So VI cos phi equal to 240 VI 0.643 cos phi 0.01072. Finally, the power consumed by this RLC circuit is 1.654 watts. And we can calculate also the series resonance Q factor. Since it is series circuit, series resonance Q factor also can be calculated. The Q factor equal to formula. We'll discuss about this topic in future in next classes. And resonance Q factor equal to 1 by R into square root of L by C. So 1 by R and L is 0.08 henries and C 8 microfarads. So finally the Q factor is also can be calculated, that is 25. Quality factor is 25. And we'll see one more numerical problem related to this RLC series circuit. So here the values of R, L and C given, and these three are connected in series to a applied voltage of 100 volts at 50 Hz frequency. So first, a series RLC circuit containing a resistance of 12 ohms, an inductance of 0.15 henries and a capacitance of 100 microfarads are connected in series across a 100 volts 50 Hz supply. So here we need to calculate the total circuit impedance offered by the circuit and impedance and the circuit's current, power factor, and also need to draw the phasor diagram. So the circuit connection with values as shown in the circuit diagram. First we will calculate the how much inductive reactance offered by the circuit. XL equal to 2 pi FL. So 2 pi into 50 Hz F L 0.15 henries. So the value becomes 47.13 ohms. And also capacitive reactance can be calculated, that is Xc equal to 1 by 2 pi Fc. That is 1 by 2 pi F of 50 and C capacitance is 100 microfarads, that is 2 pi Fc 1 by 2 pi Fc. It is value is 31.83 ohms. Immediately after calculating this XL and XC, we can calculate the how much impedance offered by the circuit. So Z equal to under root square root of R square plus XL minus XC whole square. So Z equal to square root of R square 12 square, XL 47.13, XC 31.83. So XL is greater than XC. So the net reactance X equal to XL minus XC. The net reactance offered by the circuit is XL minus XC. So here XL is greater than XC. Since XL is greater than XC, the circuit behavior is inductive in nature. So the total impedance is 19.4 ohms. And current I can be calculated as V by Z, supply voltage divided by impedance. So 100 by 19.4 equal to 5.14 amps. So voltages, we can calculate the voltages across all these three components, VR, VL, VC. So since it is a series RLC circuit, the applied voltage V should be consumed by all these three components. So according to KVL, Kirchhoff's voltage law, the sum of voltage rises equal to sum of voltage drops. Algebraic sum of voltage drops. Or the algebraic sum of all the voltages inside a closed loop is equal to 0. According to this Kirchhoff's voltage law, the voltage drop across resistance can be calculated. VR equal to I into R and VL equal to I into XL and VC equal to I into XC. So VR, the current is, since it is series circuit, so the same current will pass through the circuit. The entire circuit, the same current will flow through the entire circuit. So VR I into R, that is 5.14 into 12 ohms, that is 61.7 volts. VL I into XL 5.14 into 47.13, that is 242.2 volts. VC I into XC, that is 5.14 into 31.8, that is 163.5 volts. So total voltage, supplied voltage is drop. It is nothing but phasor sum. So the total voltage 100 volts can be obtained by using the formula VR square plus VL minus VC whole square. Also the power factor can be calculated. So for phase angle phi, the cos phi is nothing but R by Z, that is R value 412 and Z value 19.4. So 0.619 is the power factor. And since it is a inductive in nature, the capacitance value is lagging. So in previous problem, the capacitance value is leading, and this is in this circuit is capacitance type, capacitive in nature. And next problem, this problem is inductive in nature. So phasor diagram for this problem, previous problem. So VL is the 242 and VC is the 163.5 and VR is the 62. So the net voltage available across this RLC series circuit is VL minus VC. So VL minus VC is the 78.5 volts. Already VR is 62 volts. 62 square plus 78.5 square under root will give you the total applied voltage. So since the phase angle phi is calculated as a positive value of 51.8 degrees, positive value of 51.8 degrees, the overall reactance of the circuit must be inductive. So the current vector we have taken as a reference vector in a series RL circuit. The current lags the source voltage by 51.8. The voltage is taken as a reference and current lags the voltage by 51.8 degrees. So in a series RLC circuit containing one resistor, inductor and capacitor, the source voltage, that is nothing but Vs, is the phasor sum of all these three components VR, VL and VC. So if the current is common for all these, since it is a series circuit, the same current will flow through the same entire circuit. Since the current is common to all these three components, it is used as a horizontal reference. So we can use the reference as current. So when constructing the triangle, voltage triangle, we'll take the reference as current. And finally, coming to the RLC series circuit containing of multiple resistances and multiple capacitances and multiple impedances. So let us say total resistance is nothing but when multiple impedances, let us say 3 resistances are connected in series, multiple resistances. Similarly, 3 inductances are connected in series. Similarly, 3 capacitances are connected in series. Multiple resistances, multiple reactances, multiple inductances and multiple capacitances are connected in series. The total resistance and the total reactance and total reactive inductive reactance and total capacitive reactance can be calculated individually. And after that, each and every resistor is taken as one load, ZR, ZL and ZC. So we can calculate so it is also, since it is similar to previous circuit calculations, the total impedance offered by the circuit is equal to same the impedance offered by resistance, offered by inductance, offered by capacitance. The total impedance can be calculated, and also finally we can calculate the total current also. So total current equal to total voltage by total impedance. We can calculate like this. So when analyzing AC circuit containing of all the three resistors, all the three inductors, all the three capacitors, we can calculate individual impedances for resistance separately, inductance separately, and capacitance separately. We can calculate. After that, since the current is same through all the series circuit, the same current is taken as a reference for this while constructing voltage triangle. So we can find out the total phase angle also. Cos phi also can be calculated, and sin phi also can be calculated. VA cos phi will give you the total active power, and VA sin phi will give you the total reactive power, and apparent power also can be calculated by square root of P square plus Q square, which is nothing but volt amperes, denoted in volt amperes. So like this, for a series RLC circuit, we can calculate XL, XC, net reactance, impedance, current, power factor, phi, we can calculate VR, VL, and VC by analyzing the series RLC circuit. So this is all about RLC circuit analysis. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.